Artificial intelligence has created a strange problem. Companies are buying some of the fastest processors ever built, yet those processors can still spend valuable time waiting for data. Samsung believes the solution is to build memory upward. The company has revealed a prototype storage chip called V10 Bonding V-NAND, or V-NAND. It contains more than 400 layers of memory cells and uses a new wafer-bonding architecture designed to increase capacity, speed, and energy efficiency. Samsung says the technology provides approximately 58% greater memory density than its previous V9 generation. But the larger story is not simply that one chip can hold more data. Samsung is preparing for an AI industry in which storage may become almost as important as the processors performing the calculations. The first phase of the generative AI boom focused heavily on GPUs. NVIDIA's accelerators became the symbol of the race because companies needed enormous computing power to train increasingly capable models. But an AI system does not operate using processors alone. It must store model parameters, training datasets, user files, generated images, video, conversation histories, software repositories, and information retrieved by AI agents. It must move this data continuously between storage, memory, and processors. When any part of that path becomes too slow, the expensive accelerator waits. Imagine hiring thousands of highly skilled workers for a factory, but storing all their materials in a distant warehouse. The workers may be capable of producing goods at extraordinary speed, yet their productivity remains limited by how quickly trucks can deliver parts. AI processors are the workers. Storage and memory are the delivery system. Samsung's new design attempts to make that system denser and faster without endlessly expanding the physical area occupied by chips. Traditional NAND flash stored memory cells across a flat surface. As manufacturers attempted to increase capacity, they made the cells smaller and placed them closer together. Eventually, this horizontal shrinking became increasingly difficult. Smaller cells can interfere with one another, become harder to manufacture, and create reliability problems. The industry responded by moving into the third dimension. Instead of placing every cell side by side, manufacturers began stacking memory cells vertically. Samsung introduced its first commercial V-NAND generation with 24 layers in 2013. Successive generations increased the number of layers. More layers meant more bits could be stored on approximately the same chip footprint. Samsung's V10 prototype has now passed 400 layers. Visualize a city that has run out of empty land. It can either spread farther into the surrounding countryside or replace low buildings with skyscrapers. V-NAND follows the skyscraper strategy. But building a taller memory structure creates new problems. Manufacturers must drill extremely narrow vertical channels through hundreds of microscopic layers. These channels connect the memory cells and allow information to be written and read. The taller the stack becomes, the more difficult it is to keep those channels straight and consistent. Small manufacturing variations can affect performance and reliability. The wafer can also warp during production, while differences between layers can increase error rates. Samsung's new wafer bonding method changes how the chip is assembled. In conventional designs, the memory cell structure and the peripheral circuits controlling it may compete for space within the same silicon architecture. Bonding allows Samsung to manufacture different functional sections separately and then join the wafers together. One wafer can be optimized for densely stacked memory cells. Another can contain the logic circuits responsible for controlling data movement. The two surfaces are aligned and bonded into a single device. This resembles constructing the residential and transportation systems of a city separately, then connecting them through precisely placed roads and tunnels. The advantage is that each part can be designed around its own requirements instead of forcing every component into one manufacturing structure. Samsung says this approach improves density while also increasing read, write, and input-output performance. That combination is important because simply creating larger storage is not enough. A warehouse with 10 times more space does not help if it still has one small loading door. AI systems need both capacity and throughput. Training datasets can contain trillions of tokens, billions of images, scientific records, videos, and simulated environments. AI agents may search databases, read documents, call software tools, and maintain long histories while completing a task. Each operation creates more data movement. As models become multimodal, the storage burden increases further. Text is relatively compact. High-resolution images, audio, three-dimensional environments, and video consume far more space. A robot learning from millions of hours of visual experience may require enormous datasets that must be stored and accessed repeatedly. The AI industry is therefore shifting from a period dominated by model training toward one where inference creates continuous demand. Training happens when a model learns. Inference happens whenever the trained model answers a user, generates content, recognizes an object, recommends a product, controls a robot, or operates an AI agent. One training run may be enormous, but a successful model could later serve billions of requests. Those requests must access model weights, retrieve information, save results, and maintain user context. This is why NAND flash matters. High bandwidth memory, or HBM, sits close to the processor and feeds data into it at extremely high speed. But HBM is expensive and limited in capacity. NAND storage is slower, but it can store far more data at a lower cost. A modern AI data center needs both. HBM acts like the small collection of tools placed directly beside a worker. NAND is the much larger storage facility holding everything that may be needed later. The challenge is making the movement between these layers faster and more efficient. Samsung is also exploring a more radical concept called ZHBM. Conventional HBM packages are generally positioned beside an AI accelerator and connected through an advanced substrate. This arrangement offers far more bandwidth than ordinary memory, but data must still travel horizontally between separate packages. Samsung's proposed ZHBM architecture would place memory vertically above the AI accelerator. That shortens the physical distance data must travel. In electronics, shorter connections can improve bandwidth, reduce energy consumption, and lower communication delays. The approach could also pack more memory into a smaller area. Samsung claims its wafer-bonding concepts could eventually deliver more than 10 times the memory density of conventional HBM5, approximately 3 times the energy efficiency and less than half the thermal resistance. These are concept targets rather than the specifications of a mass-produced commercial product. Manufacturing such a structure reliably would be extremely difficult. Placing memory directly above a powerful accelerator creates a heat problem. Both components generate heat. When they are stacked, removing that heat becomes harder. Excessive temperature can reduce performance, increase errors, and shorten the life of the hardware. The bonding also requires extraordinary alignment precision. Connections between the wafers must be extremely small and reliable across a large chip. A tiny defect could damage an expensive package containing both memory and computing hardware. Repair is also difficult. In a conventional system, a defective memory component may be replaced separately. In a tightly bonded vertical system, multiple valuable components become physically connected. This means Samsung's vision must prove more than speed in a laboratory. It must achieve acceptable manufacturing yields, reliability, cooling performance, and cost. Yield describes the percentage of chips on a wafer that work correctly. A new architecture can appear technically impressive but remain commercially unsuccessful when too many units fail during manufacturing. This is especially important for AI hardware because the finished packages are extremely expensive. A low yield can destroy the economic advantage promised by greater performance. Samsung is also operating in an intensely competitive market. SK hynix has become a major supplier of high-bandwidth memory for AI accelerators. Micron is expanding its own HBM products. NAND manufacturers including Kioxia, Western Digital, and China's YMTC are developing denser architectures and advanced bonding technologies. Samsung remains the world's largest memory chip manufacturer, but scale does not guarantee leadership in every generation. The company has faced pressure to improve its position in advanced AI memory, particularly as demand for HBM surged. V10 and ZHBM show that Samsung is trying to compete through an integrated memory strategy rather than one product. The company wants to provide long-term storage, high-speed working memory, and future three-dimensional packages connecting memory directly to processors. This could become increasingly valuable because AI data centers are approaching physical limits. Electricity is scarce. Grid connections can take years. Cooling systems consume energy and water. Construction costs are rising. Companies cannot solve every problem by adding more servers. They must extract more useful computing from the same power and space. Denser memory allows more data to be stored in each rack. Faster data movement keeps processors productive. Better energy efficiency reduces the electricity consumed for each AI response. These improvements may sound less dramatic than a new chatbot or humanoid robot, but they determine whether those products can operate affordably at global scale. There is also a financial reason the memory industry is moving toward AI. Smartphones and personal computers created enormous demand for NAND and DRAM, but these markets are cyclical. Consumers delay upgrades when the economy weakens, leaving manufacturers with excess inventory and falling prices. AI data centers can consume much larger quantities of high-value memory per system. Samsung has said that long-term customer agreements could eventually represent between 60% and 70% of its memory sales. Long contracts would provide more predictable demand and reduce some of the extreme cycles historically affecting memory manufacturers. However, dependence on AI creates its own risk. Technology companies are currently spending extraordinary amounts on infrastructure. Their plans assume that AI usage and revenue will continue growing for years. If adoption slows, models become much more efficient, or companies discover they have built too much capacity, orders for memory could fall sharply. Memory manufacturers must make investment decisions years before knowing exactly how much demand will exist. A fabrication plant cannot be created instantly. Advanced facilities cost billions of dollars and require specialized equipment, materials, and trained workers. Build too little and customers face shortages. Build too much and memory prices collapse. Samsung's new technology is therefore both an engineering project and a bet on the future shape of artificial intelligence. The company is betting that AI will not merely require smarter processors. It will require an entirely new memory hierarchy capable of storing larger models, feeding them faster, and operating within strict limits on electricity and physical space. More than 400 layers may sound like a manufacturing milestone. Its real significance is what those layers reveal. The AI race is moving beyond the processor. Future systems will be judged by how efficiently they coordinate computing, memory, storage, networking, and cooling as one machine. A powerful accelerator without enough data is only an expensive object waiting for work. Samsung wants to ensure that when the next generation of AI processors is ready, the information they need will already be waiting directly above, below, and beside them.